Hi everyone, welcome to this video. Before I start, I'd like to thank the organizers for this opportunity to give a talk. I'm Changkeun Oh, who is a PhD student of University of Wisconsin-Madison, and I'm working with Shaoming Guo, and I'm expected to graduate in the middle of 2022. During my PhD, I worked on decoupling inequalities, restriction estimates, and some related problems. And in this video, I will talk about one of my works, decoupling inequalities for quadratic forms. And this is a joint work with Shaoming Guo, Paul Kranitz, and Lu Xiangzhang. So I'm gonna first talk about some number theory problems to motivate our main theorem. And then I'm gonna explain our main theorem. So let's start with Vinogradov's system. This is the cubic case of Vinogradov's system. It involves 2 as many variables. These are integers in this interval. And we are interested in the number of solutions. So this is the main question that we are interested in. And this problem is recently solved by Uri and Dimitrigus. So let's first calculate the lower bound of the number of solutions. So I'm gonna use this notation, J of n, for the number of solutions. And here are some trivial solutions. I'm gonna call it a diagonal solution. We set x1 equal to x1, x1 equal to x sub s plus 1. We set x2 equal to x sub s plus 2 and keep going. Then we can easily see that these satisfy these equations. So these are solutions of Vinogradov's system. And here we have as many remaining variables, and each variable belongs to this interval. So this is the number of diagonal solutions. So we have this lower bound. And here is another way of calculating the lower bound. We start with 2 as many degree of freedoms. And obviously, this linear equation carries 1 degree of freedom. And I claim that this quadratic equation carries 2 degrees of freedom. And here is my reasoning. I'm gonna call this some m. Then by this quadratic equation, m has the upper bound n squared. And if you count the number of pairs in this square, the number of pair is n squared. So these 2 numbers are equal to each other. That means generically, given n, there is only 1 pair x1, x2 satisfying this equation. That means this quadratic equation carries 2 degrees of freedoms. And similarly, this cubic equation shares 3 degrees of freedom. So to summarize, we start with 2 as many variables, and these equations share some degree of freedoms. And by this dimension counting argument, we get this lower bound. So we have proved this lower bound. And Vinogradov's conjecture says that this is indeed an upper bound. And this conjecture is proved by Uri and Dimitrov independently. And their proofs are different. And in this video, I will only talk about Dimitrov proof. And here we are only talking about cubic case, but in their paper, they proved Vinogradov's conjecture for all degrees. And this conjecture follows by decouplings for moment curves in Rn. So from now on, we will talk about decoupling inequalities. So to state decoupling inequalities, I need to introduce some notations. So we are talking about cubic case. So this is the moment curve that we will talk about. And we define surface measure on this moment curve. And here T is in this interval. So this moment curve is compact. And we decompose this unit interval into smaller sub-intervals with equal side lengths. And we define surface measure on this smaller arc. And this is the operator that we are interested in. This is Fourier transform of f on the moment curve. And by the definition of Fourier transform, we have this equality. Now we are ready to state decoupling inequalities. This is the decoupling inequality for the moment curve proved by Dimitrov. On the left-hand side, we have the whole moment curve. On the right-hand side, the moment curve is decomposed into smaller arcs, and we use L2 to sum them up. And this decoupling inequality is trivial when P is equal to 2. It's because we have this equality, and when P is equal to 2, we can simply apply Poincaré's inequality, Poincaré's theorem. And after applying that, we see that the supports are disjoint with each other. So we have a nice orthogonality, and we can easily get this inequality. And the decoupling is about what happens if we have LP norm other than L2 norm. So if we lose this number, then we can start to decompose the moment curve into smaller arcs. So here are some ingredients that Dimitrov used. Their argument relies on induction on scarce argument. And another ingredient is decoupling for parabola. At some step, the cubic term doesn't apply a rule. And what they did is to use decoupling for parabola to decompose the moment curve into smaller pieces. And the last ingredient is Braskamp-Leaf inequality. And this is very crucial in their proof. And this inequality is proved by Vinogradov in 2008. So now I will talk about more general problem. So this is the cubic case of Vinogradov's system. And now we introduce another parameter A. And this is the number of integral solutions, xi, but xi now belongs to the translated interval. And now we ask the same question, the lower bound and the upper bounds of the number of integral solutions on this translated interval. It turns out that no matter what A is, the number of solutions are the same. So this quantity is independent of A. And we call it translation-invariant property. And here is the proof. We introduce some other parameter, xi prime. What we do is to change a variable. If we define xi prime in this way, then this parameter belongs to the original interval. And after replacing xi by xi prime plus A, we get this system of equations. And if we do some simple calculations, we can easily see that this system is equivalent to this new system. But xi prime belongs to the original interval. So this essentially means that the number of solutions is invariant under translation. No matter what A is, we can translate and do some simple calculations, and we get the original system. Okay, so now we can define translation-dilation-invariant systems. Here we start with m many polynomials, and these polynomials are homogeneous. And we take all possible partial derivatives, and we add these partial derivatives to this correction, and we get a bigger correction. And this is the notation that we are going to use for the bigger correction. One example is the moment curve. We define P1 to be this part. If you take the partial derivative, we get the second last term. And if you take the partial derivative to this second last term, we get the third last term. And we just keep going. And we get this moment curve. So this is one example that we can construct in this way. So we can make a system of equations associated with the bigger correction. And we call this system a translation-dilation-invariant system. The reason is, if we construct our system in this way, then it satisfies the translation-invariant property. And also, our polynomials are homogeneous, so it is invariant under dilation in some sense. So we call it a translation-dilation-invariant system. And we can ask the same question: how many integral solutions does this system have? And this question is raised by Parcel, Prandtl, and Uri in 2012. So this is the main question that we are interested in. And here are some partial progress. Paraboloid and moment curve are two extreme cases, and these are already known by Burgen-Dimitrov and Burgen-Dimitrov-Guth. And after this work, Shaoming Guo and Ruijiang Zhang tried to generalize the theorem of Burgen-Dimitrov-Guth in higher dimensional case. And this is our main theorem. We proved decouplings for quadratic manifolds, and these are precisely TDI systems of degree 2. So I will introduce our main theorem. That's what I'm gonna talk for the rest of this video. So let's first look at some example. This is the example that I'm gonna talk for a moment. And we can think about this system of equations associated with this manifold. And if we take diagonal solutions, and if we do dimension counting arguments, we get this lower bound. And the point is that there is additional lower bound for this system of equations. The idea is we do tensor type argument, take diagonal solutions for one variable, and we do dimension counting arguments for the remaining variables. Then we get this additional lower bound. So the lower bound is also non-trivial. It depends on our manifolds. So now let's look at general cases. This is our quadratic forms. Here Qi is quadratic. And what we are going to do is to introduce some algebraic quantities. And these quantities will characterize decoupling inequalities. So this is the definition. We have quadratic forms Q, and we define the number of variables that our quadratic form depends on. And then we define this algebraic quantity. Two matrices appear in the definition. Here, matrix M restricts the domain of our quadratic form, and the matrix M prime restricts the range of our quadratic form. So we defined our algebraic quantities. So to introduce decoupling inequalities, we need to define surface restricted on similar squares. So this is our quadratic forms, and we define surface measure on this manifold. And now this is a multi-dimensional manifold. So what we do is we take squares on the domain, and then we look at the image on the function Q. So we have this smaller piece of the manifold, and we define the surface measure on it. And this is the decoupling inequality. On the left-hand side, we have the whole manifold, and on the right-hand side, that manifold is decomposed into smaller pieces. And we are interested in the loss of R. So basically, we want to find the smallest constant D of Q. And this is what we proved. This loss can be expressed as this double maximum. And this is sharp. And it took a lot of time to find this accurate expression. What we did in our paper is to introduce these algebraic quantities and proved that this is sharp, and we also proved this inequality. So I'm gonna introduce our ingredients. We still use induction on scales, and this is somehow similar to what Berger and Gus did in their work. And our manifold is a multi-dimensional manifold. So at some step, we use decouplings for lower dimensional manifolds. And the last ingredient is very crucial in our work. We used scale-independent Braskamp-Leaf inequality. And this is proved by Dominique Mardavi. And in decoupling theory, this scale-independent Braskamp-Leaf inequality can be thought of as a generalization of Braskamp-Leaf inequality. So basically, we are looking at more general manifolds, and if we use Braskamp-Leaf inequality, then we can't get a sharp decoupling. And what we did is to use more general inequality, and we were able to prove sharp inequalities, sharp decoupling inequalities by using this general inequality proved by Dominique Mardavi. So this is all that I prepared. Here is my email address. If you have any questions, please send me an email. Thank you for watching this video.